Our next speaker will be Dana Randall. She's a professor of theoretical computer science at Georgia Tech. She's known for many breakthroughs in probability, in the theory of computing, statistical physics, and most specifically for her foundational work on Markov chains. And she'll be telling us something about phase transitions today.
Well, I'm really delighted to be here, so thank you. DIMACS has had a huge impact on my career, as I'm sure many people here can say. So when I was thinking about, kind of how to frame this, especially knowing, having a sense of what Peter would be talking about, I really thought, what DIMACS really brought in the last 30 years is a real culture of interdisciplinary research and a birth of new fields that often lay between different things. So he told you a little bit about the field that I've been working in, which is statistical physics, discrete math, and computer science. He threw in probability. But what I'm going to talk to you today about is how you could apply this paradigm that he's been talking about in kind of a surprising new direction. And that is in something called programmable active matter. So when I think about continuing the journey, I now identify this triumvirate as a single field, and we're applying this single field to this new area called active matter, which I will now explain. So before I go on, I really want to thank DIMACS for giving me the birth of my career and this area. And at the time, it was one of the most coveted postdocs, and so I really had a really mind-opening experience here. For this, I want to also thank the NSF Algorithms in the Field program, which really got this whole area started. Okay, so programmable active matter, the idea is that you have a lot of, we could think of it initially as just particles that are moving around or trying to do something, and you're trying to get them collectively to accomplish a specific task. They often are local, they just know their local neighborhood, they don't have a lot of computational capability, it's a distributed setup. So you've seen this in DNA computing probably, and there's all sorts of models in swarm robotics. And we're going to view this as a self-organizing particle system initially. So this is the theoretical end of it, where each of the particles has constant memory. So particles in the system don't even know how many particles are in the entire system, okay? And they're fully distributed and local and asynchronous and so forth, okay? And our goal is to get them to accomplish tasks. So the tasks I'll be talking about later on are things like, if you have a collection of these particles, how do you get them to compress, to find each other and gather in a small neighborhood? Each one just sees its local neighborhood. How do you get them to all align in a certain direction and flock, and so forth? Okay, so I will show you examples of this later. So why simple algorithms? So first of all, you could imagine this truly is a distributed problem where you have these robots that are just each doing their own thing and are trying to collectively do something. But what's interesting here is I've coupled with a couple of experimentalists. So later on, I will be showing you algorithms on these completely primitive setups. One of them is Bobbots, which is one of the models from Dan Goldman's lab. He's a physicist at Georgia Tech. And these are really dumb and badly made. I usually use a different word besides bad. And these are syn cells. So Michael Strano is a chemical engineer at MIT. These robots are the size of a red blood cell. And we need simple algorithms because we want red blood cells to compute, which is, really like energy is a big constraint. And I will show you this at the end of the talk. Okay, so the setup for the initial part, the self-organizing particle system, is called the Amoebot model, which is trying to capture this distributed setup. So we have the triangular lattice, we have a bunch of particles. They move by expanding, deciding whether they want to be there, and then contracting, okay? So they do some local computation. Particles, again, constant size memory, they communicate only with adjacent particles. There's no common orientation, but they do have a common chirality if we need it in the model. And we're going to assume that the particles stay connected initially. Okay, we're going to relax this later on. Okay, so here we have a component of particles. And there was a bunch of work that was done previously on the Amoebot model, coding a surface, leader election. These are very challenging when you really have this limited view of the world. And the one that we set out to look at was called compression. So you start off with some connected configuration, which is clearly not collected or compressed, and you want to end up with something like what's on the right, okay, which is compressed, so you have to figure out what the right definition is. You see this behavior in nature. How do honeybees, ants do this, okay? And the converse problem is expansion. So how do you get a collection to expand, all right? So the compression problem, the way we define what we're trying to do is we say that a configuration is alpha compressed if the perimeter is within an alpha factor of the minimal possible perimeter when you have maybe a hexagon, okay? So clearly, this is going to be a linear perimeter, and this is going to be a square root, okay? So order square root. So here is our algorithm. This was open in distributed algorithms for a while. People were trying to figure out how to do this. And this is completely born out of this idea of statistical physics meets computer science. So we have moves that keep the configuration simply connected. That was the hard part, okay? So just showing that you could reach every configuration, and we had to have a set of rules where we basically just throw out every move that could be ambiguous, that could possibly disconnect or create a hole, and we show that we are still connected. We use Poisson clocks for particles to wake up and move asynchronously. And finally, we use what's called metropolis probabilities that get this entire configuration to converge to the distribution, which is lambda for some given lambda, raised to the number of edges, so nearest neighbor particles, okay? So just as Peter was showing before, when lambda is large, this is going to favor things that have more internal edges, and it suggests that it should be compressed, and in fact, this is what you get. Okay, so this very simple algorithm where we're just favoring, things are moving stochastically, they could increase the number of edges, but you want to favor things where they're compressed. So, whoops. Can you help me get back? Thank you. All right. I'm not far in, so. I could get there. Okay. I will not do that again. Okay, so here we see that, pretty quickly you see this compression happening, and if you ran it a lot longer, it would pretty much stay compressed, although it would keep moving. And so, there was a lot of big deal. You just have, you're favoring, you have, this pull between them. Of course, it gets compressed. When you do this with two, you never get compression. You could run this forever. The thing is never going to compress. Okay? So maybe this is, not surprising after Peter's talk, but we were able to prove some theorems. So this gets switched when I give someone else my thing. This says 2 plus root 2. So we show that when lambda, so we prove that when lambda is greater than 2 plus root 2, you in fact get alpha compression, where alpha is in terms of lambda. And it's not a terrible, if lambda is 4, alpha is 9, okay? And we prove the converse, which says that if you're less than 2.17, you not only do not get compression, you actually get expansion. So for expansion, you're within a constant factor of the maximal linear arrangement, okay? So there are these two different phases, and this is what we prove, that there's no compression and actually an expansion, and then after a certain point, we have compression. And we don't know what happens in the middle, but for this type of problem, we don't really care, so it's okay. Okay. And we could actually relax connectivity, which is going to be important for the applications. And I'm not going to say a lot about this, But it's almost the same algorithm, only we don't have to worry about maintaining conductivity anymore. We're just having particles move around, and we're favoring more edges in the stochastic way. And we have a more complicated definition of what it means to be aggregated rather than compressed, because we want the particles to come together. And it basically says that there's a nice region with linear perimeter, quadratic area with the majority of the particles inside, okay? And we get a similar theorem. Okay? And it turns out that this paradigm, before I show you all of this in practice in terms of the actual experiments, I'm going to just show you that there are other really natural algorithms that you might want to achieve with these collective behaviors. So I talked about compression. You have a community that wants to gather. Separation is, you could imagine two different species of ants that under favorable circumstances are all mingling. And then when circumstances get bad, they want to separate into their own species. Alignment is sort of flocking. How do you get them to point in the same direction and possibly move? And locomotion, this is a weird picture for locomotion, but you'll see in a minute why I have that picture. Okay. So alignment. This, I'm going to tell you up front, is a completely gimmicky toy model. We have other things that probably are going to behave better, but this we could prove something about, so I'm just going to show it because it demonstrates, I think, an important point. So here, the specifics are not so important, but we have vertical blue diamonds and horizontal orange diamonds. They move by stretching out, so a vertical becomes a horizontal as it's moving and vice versa, so these things slosh around. And I'm just going to show you, actually I need the computer to start these animations. Can you just like click the two arrows, yeah, underneath if you hit start? Okay, so this is just some value of lambda in our model. Now you could start the other one, please. This is a slightly larger value of lambda, okay? So these are very small, similar parameters, and you see really different behavior. And you see different behavior because this is exactly the independent set model that, the hardcore model that Peter just talked about. This is above 3.79, and this is below 3.79, okay? So you could imagine a setup where these things are self-regulating. So in the case of compression and expansion, you could imagine foraging, and you could think of lambda as responding to food, right? So you have a food source, lambda goes up, everyone compresses around the food source. Then you deplete the food source, lambda goes down, it's like a hormone, everyone gets hungry, and you expand until you find new food source, and then you could compress again. So you can have this sort of self-regulating property, okay? Separation, again, this was, you have different species of ants. We show that there's two parameters, one for compression, one for separation, and here are the four pictures of compressed, not compressed, and separated and integrated. And you could see they're doing exactly what you would expect them to do. Okay, so this is the fun part, which is how do we actually implement our algorithms in the real world? So first I'm going to start with Bots, which is a collaboration with Dan Goldman's lab. Okay, so these are behaving, oscillating, buzzing bots, named after Bob Behringer, which is one of the founders of this collective behavior. So here, this is what bots do. They are crappy little robots about this big, about the size of a hockey puck, and they have motors that cause them to vibrate, and we put magnets around the periphery, okay? And the motor creates random motion, the magnets delay detachment. So I described the compression algorithm as favoring attachment, but more magnets mean when you have a lot of neighbors, you have smaller probability of detaching, which is exactly the same as favoring going to places with more magnets. The Markov chain is identical, the analysis is identical, okay? But the advantage here is that these things have no computational capacity, no memory, they're dumb and badly made. So the point is that these algorithms are pretty robust, right? It doesn't matter that they're not exactly doing the algorithm. And so let me just get to the point. Our prediction was that we would get compression and no compression. So we have experiments with these running around. We expected with the stronger magnets you would get them compressed. We have simulations so that we could scale up because we can't build so many of these so easily. So here they are. Hopefully I can get this to go. Okay, so the low magnetization, you know, little clusters come together, but you don't get large compression. Over here you see compression. We have evidence of exactly the phase transition that we predicted. But then we had this question of, so what? Okay, so why is this interesting? So we came up with the following task. So we have these Amoebots, and we have a foreign object in the middle, and we say go. And we do this with small magnets, with weak magnets, and with strong magnets. So here are the weak magnets, and they're hitting it, and they just can't generate enough force. But then if you look at the high magnets, they can successfully clear the objects. So unfortunately, it's a little bit hard to change the magnets each time you want to do this, but what you can do, instead of keeping the motor strength the same and changing the magnetic strength, you could do the opposite. So you could fix the magnetic strength and make the motor stronger or weaker, which has exactly, again, the same effect. It's the same Markov chain. And so they built these now with a light sensor. So when the light is on, these things move faster, and when the light is shielded, they move slower. So you could change from compressed to expanded just by changing the light, which is potentially useful. We don't really know exactly why, but we could clear things. Okay, so syn cells. This is, has been really fun. So there's, again, these are going to be red blood cell-sized, quote-unquote, robots. So I'm going to pretend I know something about chemistry, which I don't, but these are graphene laced with platinum in a bath of hydrogen peroxide. So what happens in the hydrogen peroxide reacting with the platinum is that bubbles form, and these bubbles cause motion. Okay, so we get these things moving around a little bit. We also can put iron oxide around the outside, and that gives this little magnetic push. So we have the two things that I need for my algorithm, which are interparticle interaction, this attraction, and this dispersion potential. Okay, so this says the same thing in more detail, but yeah, okay. So the prediction is that this is going to behave very similarly to what you saw with the Amoebots. And we expected this phase diagram. I'm saying it as though we don't get it. We do get this under the right circumstances, where the rattling propensity is how much hydrogen peroxide there is, controls how much these things rattle around. Okay, so that's the motor. And the interparticle interaction, this is what the iron oxide is doing, okay? So in some middle phase, we expected that we would be able to dynamically change between these two settings. We found something really surprising. So you can get exactly this. You could also get the following. So this is 5 syn cells. Okay, these are 5 cells made of just what I told you, nothing else. And they're doing the compression algorithm. But what was unexpected is that this bubble pops. Okay, so you get these things pulling together, the bubble pops and pushes them back apart, and then they start coming together again. And we found that even without the iron oxide, what's known as the Cheerios effect, this says if you have things on a liquid surface, the surface tension tends to pull them together. So it turns out we don't even need the iron oxide, okay? So we did some analysis. They did some analysis. This is Michael Strano's group. This is 0 seconds, 2 seconds, 4 And we went a step farther and looked at the Fourier analysis of it, and you get ridiculously regular oscillation. Okay? So I'm going to go back and just show you this again. So I'm not going to be political, but I am. I come from a state which has a heartbeat law. So you tell me if you think this is anything significant. If you tested this with an ultrasound, you would hear a heartbeat. Okay? So I find it quite remarkable that you can do this with 5 red blood cell-sized cells, and you could get this dramatic effect. So I have to say, we don't really know what to do with this. Right now, it's just phenomenological. But potentially, this can give us some sort of synchronization, some sort of clock, and we're looking at how this scales up. And we expect you're not going to have this uniform synchronization, but it can give us something that's going to allow us to compute. And Michael Strano is now building batteries and various ways to conserve energy with these syn cells. So there's very interesting work going on there. Okay, the last thing that I'm going to talk to you about is not my own work. We did a little bit on this, but this is in Dan Goldman's lab. He has these things called smarticles. So this is really what started this whole collaboration. Smarticles they look like staples, and you blow a whistle, and they start swinging their arms back and forth. And that's all they do. So they're named for smart particles, okay? But in fact, the beauty of them is that they're really dumb, so it was not the best name, okay? And so you take one, and it just starts moving its arms. I'm going to show you a video in a second, where these guys move their arms, but this thing doesn't move anywhere. But then he took a bunch of them, and he put them in a ring. And suddenly, like anyone who has kids in elementary school, they start jostling each other and this thing starts moving, even though one by itself can't, okay? So, moreover, at one point, a battery died, okay? So if you see this thing, and you'll see it in a second, jostling around, you get something like Brownian motion. We've done an analysis, where the thing is moving, but pretty much staying where it is. But when one of them died, they noticed that there was drift towards the dead particle. Okay, so here is their movie. So you see the single smarticle on the side. They play the sound that starts all of them moving. So the one on the left is not doing anything at all, and the ones in the ring are pushing against each other, pushing against the ring, and you see the center of mass trajectory. And now they kill one of them. And they speed it up, and you'll see a very different trajectory where in this particular instance, it's not going exactly towards the dead one, but in general, they do. So we've done experiments where we can freeze them by shining a light. So you have a bunch of these, and you shine a light, and shining the light freezes anything that sees the light, so we can get things to move towards the light. You could also change the coefficient of friction and get things to move away. So again, I'm not sure why we want this, but we're trying to explore how, if you have these really dumb things interacting together, you can get this emergent behavior. And the emergence in all but this last one are completely from this phase transition, where we're on one side and we get one behavior, and we're on the other side and we get a different behavior. Okay? So let me just put these all up. So there are lots of directions that we're continuing this work in. Really what we're trying to understand is what is the minimal computational requirements to achieve a given task. So in computer science, you're starting with a various kind of model, and you're saying, okay, in this distributed system, I have this kind of memory and this much computational power. We really are trying to understand, without that, what is the minimal thing that we can get? And in the case of compression, in some sense, we were able to eliminate all of the standard computation. And we made all of the computation happen by this mechanical interaction, which is what you're going to need in order to get things to scale to these really tiny quote, robots, okay? So the second is discovering what tasks could be accomplished. So I showed you a whole bunch. I showed you separation and alignment. And the point is, for all of these, we really started with statistical physics models where we could rigorously prove things, okay? And, you know, we sort of have to get away from that a little bit to sort of really understand the full potential of what this kind of programming can do. And finally, use non-equilibrium physics tools. So in these systems, the robots are driven. The moves are not really reversible, so we really need a lot of new mathematics to understand what's going on. And to answer your question from before, where we are getting this interesting emergent behavior, it's exactly when you're on the wrong side of the phase transition. It's exactly where things in the traditional sense are slowly mixing. But we're not looking for a random sample, we're looking for a typical sample. And what we find for these is that you very quickly get to near some ground state. It's just going to take an exponential time to get to a different one, but we don't care. So, you know, new analytical tools for these sort of meta-stable states, there's a lot of math that's still needed. So, thank you.
Any questions?
As you hinted when you said you were going to be a little political, this is kind of wonderful. There are philosophers who try to understand where life can come from, and once you get this collective behavior that you were able to attach a name to, you say, good grief, these cells now have an intention. It's quite beautiful.
Thank you. Yeah, I agree. Yeah.
Hi, Lou Gross, University of Tennessee. Thank you very much. There's lots of connections to what you talked about, this whole field of complex adaptive systems and agent-based models. So a specific question. In agent-based modeling, there's attempts to basically overall control a system by controlling space. Think of it as temperature underlying how rapidly things move. Is there a body of theory that you all have worked on that allow you to think about how to effectively control by controlling space here to lead to particular emergent phenomena?
So we have this team of people from, you know, our newest project is now supported. The experimental side of this is supported by AMIRI, which is the Army. We have 6 PIs. One is a theoretical physicist who looks at origin of life questions, as you just mentioned. We're throwing a lot of tools at this, but depending on who you ask, the whole idea of this whistle that starts the smarticles going, we don't want that, right? I mean, if you're studying distributed systems, you want to get rid of the puppeteer altogether. So we're trying to understand, one, what we could do if we're allowed to cheat a little bit and change the temperature or have different pockets that are behaving differently is definitely one of our goals. The computer scientists, there are 2 of us on this project, we really want a really self-regulating system. So a system, but still, you know, like when I mentioned the foraging example, they're responding to the environment by noticing the food is depleted, and that changes their state. And some of them go to the new state, and some don't know yet. And so these are the theoretical questions we're asking. But I mean, both directions are interesting. I mean, I think that I would love to talk to you because I think you have a whole field of stuff. I mean, really, what DIMACS gave to me and many other people is a bit more of a fearlessness of going into other fields and seeing how things connect. And this is DIMACS' legacy, which I am very grateful for. And maybe I'm taking it a little too far here, but I'm very grateful for the start. So,
Thanks.
Thank you.
Is there time for another one?
Any other questions? I've got a slightly more pedestrian question. So I just couldn't help but notice that with your smarticles, the particles were quite large compared to the size of the universe. Do you know what happens when they're tiny in comparison to the universe?
Well, again, this is like literally a robo-physicist experimenting in the lab with crazy students, and you take the ring away, you get the same effect. So all it takes is these things kind of clamping around each other. And you get interesting behavior. So there's all sorts of theories about these pockets of, it's called least rattling, which is why we're using this term. Jeremy England is another physicist at MIT, is a theoretical physicist who looks at origin of life, who has this theory, and they're finding that these things settle into kind of these metastable configurations. They wouldn't describe it that way, but so we do know a little bit about how it scales. But the problem is, as soon as something disconnects for the smarticles precisely, they freeze, right? So, but they persist in staying attached much longer than you would expect. So even without the ring.
No further questions. Let's thank Dana again.
Thank you.